Hello everyone, my name is Ankur Gupta. I'm a postdoc in the Applied Computing for Scientific Discovery group. Today I will talk about the 3D deep learning models we developed for predicting molecular properties. Every known and unknown medicine and material exists in this so-called chemical compound space. However, it is incredibly huge. According to some estimates, there are around 10 to the power of 180 compounds in the chemical compound space. Now, to find compounds or molecules for a particular application or having a desired property, we usually have to compute their properties at high accuracy levels. For example, to find a drug molecule, we typically compute the binding strength of a set of drug-like molecules to the target protein, which can be computed accurately using quantum mechanical methods. However, most highly accurate quantum mechanical methods are extremely slow and computationally expensive, and thus are not a viable choice to explore the chemical compound space. On the other hand, machine learning techniques could provide a feasible way to compute molecular properties quickly and accurately. Therefore, there is a need to develop novel and accurate machine learning models to enable the fast discovery of new drugs, catalysts, and other valuable compounds and materials. Now, one of the reasons we are interested in developing 3D machine learning models is because molecules are intrinsically three-dimensional in nature. We are interested in predicting a wide range of chemical properties using machine learning. Therefore, we would like to test new descriptors that could simultaneously capture the molecular and electronic structure of the molecule in its native 3D environment. And since molecules are three-dimensional, quite a lot of features associated with a molecule could be represented in 3D space better. However, such 3D features have been relatively unexplored. Therefore, I will discuss the efficacy of some of these new 3D molecular descriptors in my talk. Now let's talk about quantum mechanical methods in general. There's a sort of hierarchy where we have computationally cheap and relatively inaccurate methods at the bottom of the rung and highly accurate but very expensive methods at the top of the rung. So if we compare wave function-based methods and density functional theory, then from this hierarchy diagram, we can clearly see that the wave function-based methods are much more accurate than DFT. However, they are also computationally expensive. On the other hand, DFT remains the most popular method in the quantum chemistry community. For example, it is the primary workhorse for the materials project. DFT in general is computationally cheaper than the wave function-based methods, but it could be error-prone. Therefore, there is a need to develop frameworks to make DFT calculations accurate or get more accurate results at DFT cost. Therefore, we would like to find a way to attain wave function method level accuracy at a much reduced cost. One way to achieve that is to use the so-called delta machine learning method, and thus we have adapted it in our work. In the delta machine learning scheme, we train the model to predict the energy difference between a high and a low level of theory. Therefore, if we know the energy at the cheap level of theory, we can compute the energy at a high level of theory using this equation, where this delta energy term is predicted through our machine learning model. Now it's easier to understand how molecules could be represented in 3 dimensions if we first see how 2-dimensional images are stored and represented. We know that every 2D image is composed of pixels, and each pixel is a combination of red, green, and blue colors, as you can see in this figure. Now, if you want to perform a machine learning task on such images, then they need to be converted to a computer-readable array. So if we have, let's say, an image of a dog like this, then it can be represented in the form of a tensor whose dimensions would be pixel width by pixel height by the number of channels. The red, green, and blue colors are the channels in this case. Therefore, this last dimension is 3. In the same manner, we can imagine a molecule to be a 3-dimensional image. So for a molecule, we can construct a grid in the 3-dimensional space onto which the atom positions could be embedded. Similar to 2D images, these grids can be imagined to be made of 3D pixels, which are formally called voxels. So this molecule would look something like this in the grid format. Here I have shown only a binary representation, which means that the occupied voxels have ones in them, and the unoccupied ones are all zeros. And since all the atoms are in a single channel, the tensor shape of this grid is 15 cubed by 1. This means that there are 15 voxels along each spatial grid dimension, which is formally known as the grid length. Alternatively, each atom type can have its own separate channel. For example, this is how the hydrogen channel would look like for this molecule. For this representation, the tensor shape is 15 cubed by 4, since there would be 4 channels corresponding to different atom types in the molecule. In short, one can store useful chemical information associated with an atom in a voxel corresponding to its spatial position. So theoretically, any property associated with an atom could be used as a quantity to encode its chemical information in the 3D grid. For example, it could be atomic charges. We can also potentially use quantities like the number of bonds connected to other atoms, atom type, etc. However, a major issue with 3D discrete voxel data structures is their intrinsic sparsity, which in turn may lead to an underfitted model due to the lack of enough information to learn from in the input representation. There are quite a few techniques available in the literature to reduce the sparsity of a 3D data structure. For example, we can reduce sparsity to some extent by convolving the 3D molecular image with a Gaussian or a wave transform filter, which imparts smoothing or a blurring effect to the input representation, which also helps capture the interatomic interactions approximately. Additionally, we also have memory-efficient data structures, which are inherently less sparse than the standard voxel-based data structures. For example, in the octree data structure, as shown in this figure, only the non-sparse regions of a cubic volume are recursively partitioned into finer resolution octants, due to which the sparse voxels are relatively fewer in number. In this work, we have developed a new way to minimize the data structure sparsity by using intrinsically dense molecular descriptors. In other words, we are using a volumetric property associated with the molecule. Broadly speaking, volumetric functions for molecules could be divided into two categories. First, energy-based functions, for example, electrostatic potential energy due to nuclear charges. Second, electron density-based functions, which depend on the electron probability distribution and are derived from the electronic wave function of a molecule. In this work, we are mainly interested in testing electron density or wave function-based volumetric functions, as they encode the geometric and electronic structure of the molecule simultaneously, and hence can be used to predict a wide range of molecular properties. Localized orbital locator and electron localization function are the two most popular electron density-based functions, and we have used them as descriptors in our machine learning model. Both localized orbital locator and electron localization function work on the same principle. As the name suggests, electron localization functions quantify electron localization or distribution in a molecule. So physically speaking, the localization function values are closer to 1 in regions where the electrons are highly localized, such as atom cores and bonding regions. On the other hand, the associated localization function values are closer to 0 for electron delocalized regions. Such regions are usually found near the periphery of a molecule. And from this figure, we can get an idea of how the electron localization function partitions the molecular topology into electronically dense and diffuse regions. And for the sake of visual comparison, a discrete voxel-based representation of the same molecule is also shown here on the right. These images clearly show the difference in sparsity levels between the two representations. Now, once we have the input representation of a molecule, we would like to learn patterns across different molecules in the dataset and correlate it with a desired molecular property, which is energy in our case. Since our input representation of the molecule is a grid-like data structure, we used a convolutional neural network as our model architecture. Convolutional neural networks use convolution layers as building blocks, where a small kernel window slides across the image as shown here and learns the patterns in the image. The numbers in this kernel are nothing but the learnable parameters of the neural network. I have shown a 2D example here for simplicity, but the same idea applies to 3D images. In this work, we use the DenseNet convolutional architecture, which is quite popular in the deep learning community and is commonly used for computer vision tasks. We modified and adapted the standard DenseNet architecture accordingly to make it compatible with 3D input representations and for the grid sizes in our work. This figure here shows the base DenseNet architecture that we used in this work. But the most important feature of DenseNets that we need to understand is this dense block, which is composed of these dense layers, which are not to be confused with a fully connected layer, which is also called a dense layer in some books. These dense layers are made of convolutional layers that I discussed earlier. And the defining trait of a DenseNet architecture is the dense connectivity pattern inside a dense block, as shown here. In a dense block, every dense layer is connected directly to every other dense layer through a concatenation operation. So the feature maps generated by a dense layer are concatenated with those produced by all the preceding layers, which are then passed as an input to the next layer. In this way, the features learned by the shallower layers are transferred to the deeper layers, which enhances the learning process. Therefore, in this architecture, one of the most important hyperparameters is the number of dense layers in each of the dense blocks, as it determines the overall depth of the architecture, which ultimately determines the model's overall performance and training cost. So we experimented with different dense layer configurations for this architecture, as I will show in the next few slides. The model performance usually depends on a number of model and data related hyperparameters. Therefore, in the next few slides, I will talk about the effect of varying some of the key hyperparameters in my model. The input tensor shape and size depend on the grid length or resolution, which also determines the quality of the topological information encoded in the grid. Moreover, the training cost associated with the convolutional neural network scales as the cubic power of the grid length. Therefore, selecting an appropriate grid length is quite important if the computational resources are scarce. For this plot, we generated the descriptors with different grid lengths, 12, 14, and 16. These input representations are then used to train the DenseNet architecture with a dense block configuration of 16, 16. This means that there are 16 dense layers in the first dense block and another 16 in the second dense block. And the results clearly show an improvement in model performance with an increase in grid length, which makes sense because the higher the input grid resolution, the more detailed interatomic features would be available to the model to help it distinguish between different molecular patterns. The best result in this plot is 0.42 kilojoule per mole, which is better than the previously reported results using the delta SNET and delta FCHL models for the same data set. On the other hand, DFT has an error of around 17 kilojoule per mole with respect to the wave function theory. Therefore, quantitatively, all errors from our machine learning models are very small, making these results quite impressive and encouraging. We also tested our model by varying the network depth or changing the dense block configuration. So we tested the model performance by simultaneously doubling the number of dense layers in each of the dense blocks. The best performing and also the most expensive model we tested has a dense block configuration of 32,32, since it has the most number of dense layers. And for this model, we get an MAE of 0.39 kilojoule per mole. Therefore, in summary, we can systematically improve the model performance by increasing the depth of the architecture, which, however, is also accompanied by an increase in the training cost. In our work, a single descriptor proved sufficient to provide excellent accuracy levels. However, in more challenging problems like protein ligand binding energy predictions, we may have to combine a large number of molecular descriptors to form the input representation. Here we tested whether the model performance would increase further if we provided more learnable features to the network. As shown here, it turns out that the mean absolute error did not reduce much. This is potentially due to information overlap between the three topological descriptors, which could mean that we are adding redundant features to the input representation. It is also possible that the test error has already been saturated with respect to the network architecture and could mean that a deeper or a wider architecture is needed. Finally, in this work, we tested only 3 topological descriptors, but we plan to test other discrete and dense descriptors in the future. Now let's talk about incorporating rotational invariance in the model. We know that a molecule can attain multiple orientations in the 3-dimensional space. However, convolutional networks are not invariant to rotational transformations of the input object. Therefore, to reduce variance in the machine learning model with respect to the input rotations, we incorporated data augmentation during model training. Specifically, we transformed the input object or the molecule through all possible combinations of 90-degree rotations, which yielded 24 different orientations. This means that both the training and test data sets increased by a factor of 24. Now we trained the same machine learning model using the augmented and the unaugmented data sets separately. And from the results, it is quite apparent that data augmentation significantly improves model performance and generalizability, and thus should be incorporated in the machine learning model. So how did we do compared to some of the other models in the literature? In summary, for the QM9 dataset, which is a collection of molecules with at most 9 heavy atoms, our model clearly outperformed other models in the literature. In addition, for the dataset with slightly larger and heavier molecules, the DenseNet model is comparable to the delta FCHL model. However, the delta FCHL model is a kernel-based method, and thus its inference time scales poorly with large training datasets. Our DenseNet model, on the other hand, is a deep learning method and therefore could be easily used with large training datasets. So to conclude, we developed a 3D deep learning framework to predict energies at very high accuracies. To resolve the issue of sparsity in 3D data structures, we used quantum chemically derived, physically meaningful electron localization functions like ELF and LOL as molecular descriptors. The results we obtained are comparable or better than the previously reported results for the same data set. We also tested the model's efficacy with respect to several key hyperparameters, some of which helped improve model accuracy in a systematic manner, like grid length, grid resolution, and network depth. So finally, in this work, we have proposed a general method that can be used for a wide variety of molecular properties. For example, electron localization functions have also been used to study bonding in open shell systems and transition metal complexes. Therefore, machine learning models based on electron localization functions can be a highly valuable tool to predict the properties of systems where the electronic structure is known to play a key role. I would like to thank Bert and all members of the ACST group at the Berkeley Lab for all the help. I would also like to thank all members of the Raghavachari group at IU. Thank you for listening, and I would be happy to answer any questions.